Let's practice determining whether the following series converge or diverge. Let's look at the series n equals 1 to infinity of n factorial, n plus 1 factorial, n plus 2 factorial, all over 3n factorial. And the question is, can we make some sense out of what this is saying? So n factorial is going to be 1 times 2 times 3 all the way up to n. And then n plus 1 factorial is going to be 1 times 2 times 3 times all the way up to n times n plus 1. And then n plus 2 factorial will be 1 times 2 times 3 times times n plus 1 times n plus 2. And then on the bottom we're looking at 3n factorial. So this is going to be 1 times 2 times 3 times times n plus 1, but it's going to keep going times 2n. It's going to keep going times 3n minus 1 times 3n. Alright, so it looks like, just from looking at this, the bottom looks a lot bigger, but it's really kind of hard to tell. The bottom certainly has bigger numbers in it. So let's figure out what kind of test we would want to use. Let's try the ratio test. Factorials usually are a good time to do the ratio test. Now the only thing we need to check is that all the terms are positive, and they are. It's all made out of all positive numbers. Alright, so we want to look at the limit as n goes to infinity of a sub n plus 1 divided by a sub n, which I'm actually going to write the a sub n already flipped over. So first we'll write a sub n plus 1, so that's n plus 1 factorial, n plus 2 factorial, n plus 3 factorial, divided by 3 times n plus 1 factorial, times, and then a sub n's on the bottom, so we'll flip it over. This is n factorial, n plus 1 factorial, n plus 2 factorial, over 3n factorial. Now we can quickly see that the n plus 1 factorials cancel and the n plus 2 factorials cancel. So let's rewrite this as the limit as n goes to infinity of n factorial times n plus 1 times n plus 2 times n plus 3, that's rewriting n plus 3 factorial, divided by n factorial on the bottom, times, and now we have 3n factorial on top, and on the bottom we're going to rewrite 3n plus 1 factorial. So first of all, notice that this is 3n plus 3 factorial. So if we start at 3n factorial, we also have 3n plus 1, 3n plus 2, and 3n plus 3. Now simplifying again, we can cancel the n factorials and the 3n factorials. And we are looking at the limit as n goes to infinity of n plus 1 times n plus 2 times n plus 3 all over 3n plus 1, 3n plus 2, 3n plus 3. And the coefficient on the top, the largest coefficient there, is going to be an n cubed. And on the bottom, the largest coefficient is going to be the 3n times 3n times 3n, so that's 27n cubed. So this limit is going to give us 1/27. 1/27 is less than 1. Therefore, the original series, n goes from 1 to infinity of n factorial times n plus 1 factorial times n plus 2 factorial over 3n factorial converges. Let's try another example. Let's look at the sum n equals 1 to infinity of the square root of 2 minus 1 to the n. Now this looks kind of strange, but after staring at it for a minute, you'll realize that this is really geometric. It's just a number r raised to the power n. In this case, r is going to equal square root of 2 minus 1. So now we need to know something about the square root of 2. We know it's a number that's between 1 and 2. It's like 1.7. So 1.7 minus 1, this is going to be approximately 0.7, and it's less than 1. So this series converges. Let's try another example. Let's look at the sum. N goes from 1 to infinity of e to the 1 over n divided by n squared. Now this series, the first thing we want to check is the divergence test. What is the limit as n goes to infinity of e to the 1 over n squared? Well, e to the 1 over n, well 1 over n goes to 0, so this is e to the 0, so this is 1 on top. And then n squared goes to infinity, so this whole thing is equal to 0. Okay, so the divergence test doesn't help. So what else can we try? Well, it's not geometric, it's not a p-series, it's not a harmonic series, so it looks like we could either have the integral test or the root or ratio test. I don't really want to integrate this. Actually, no, maybe it wouldn't be too bad. I could integrate it. This could be u, and then the derivative of u would be 1 over n squared negative. So I would actually, integrating this might not be so bad. Let's try the integral test. Problem with the integral test is we have 3 hypotheses we have to check. So we need to know, is our corresponding function f of x equals 1 over x squared, e to the 1 over x. We need to know, is that continuous? And it is continuous for x bigger than 0, so it's continuous for x greater than or equal to 1. Is it positive? It's always positive. E to a power is always positive. X squared is always positive, so it's positive for x greater than or equal to 1. And now we need to know if it's decreasing. So let's take the derivative. F prime of x is equal to, let's write this as x to the negative 2, then we can do the product rule. I'll write this one as x to the negative 1. Alright, so the derivative of the first term is negative 2, x to the negative 3, times the second term unchanged, plus the first term unchanged, times the derivative of the second term. So that would be e to the x to the negative 1 times the derivative of x to the negative 1, so that's negative 1, x to the negative 2. Alright, so let's see if we can simplify this. So we have negative 2, x to the negative 3, e to the x to the negative 1, plus, actually minus, because there's a negative sign over here, so minus x to the negative 4, e to the x to the negative 1. And we can pull out an x to the negative 3, e to the x to the negative 1. And we're left with negative 2 minus x to the negative 1. Well, this is a positive number because x is bigger than or equal to 1. This is a positive number because e to any power is positive. And this is a negative number because remember x to the negative 1 is 1 over x. And this is going to be positive. So a negative 2 minus a negative 1 over x is a negative. So positive times a negative is a negative number. Alright, so now we've got continuous, positive, and decreasing. So let's look at the integral from 1 to infinity of e to the 1 over x squared dx. Rewrite this, since it's an improper integral, as the limit as t goes to infinity, the integral from 1 to t of e to the 1 over x squared dx. And we're going to do a u sub over here to the side, so let's do some scratch work here. U equals 1 over x, du equals negative 1 over x squared. So our integral becomes a negative sign out front from this, negative e to the u du. So we know we're going to get negative e to the u plus c is the antiderivative. So going back, that means that our original integral is the limit as t goes to infinity of negative e to the 1 over x evaluated from 1 to t. Note I always do the u sub off to the side when it's an improper integral. I don't want to have to think about how the bounds would change since the bounds are going to infinity. So it's easier just to find the antiderivative and then go back to the original x. Okay, so rewriting this is the limit as t goes to infinity, negative e to the 1 over t plus e to the 1 over 1. And 1 over t again goes to 0, so negative e to the 1 over t becomes negative 1 plus e. So we're getting e minus 1 as our answer, so that converges. So our series, k going from 1 to infinity of, I guess we used n in this one, right? N going from 1 to infinity doesn't really matter what letter, right? E to the 1 over n divided by n squared converges by the integral test. All right, let's look at the series k goes from 1 to infinity of 1 plus 1 over n to the negative n squared. Now, this one we might want to try the divergence test on first because I can't obviously see what that limit's going to be. Well, this doesn't make any sense. We can't have k's and n's, so let's make this one n. Okay, so 1 plus 1 over n to the negative n squared. And if I look at the form of this answer, this is going to go to 1, it's 1 plus 0, 1 to the negative infinity. So that's kind of like 1 over 1 to the infinity, but 1 to the infinity is an indeterminate form. So we want to rewrite this so we can use L'Hopital's rule. So write this as the limit as n goes to infinity of, you know what, we could keep doing this, but in this particular case, I think that it might be faster to do the ratio test. So this is the divergence test, and we'll come back to this if I'm wrong. But, you know, on the test, we want to be fast when we can. So we're going to change our mind, and we're going to look at the root test. I might have just said ratio test, but I meant root test. Because if I do the root test, I can take the nth root, I'll get rid of one of these n's here. So let's look at the limit as n goes to infinity of the nth root of a sub n, which is the limit as n goes to infinity of the nth root of 1 plus 1 over n to the negative n squared. And I should also mention that to do the root test, I had to check that it was positive, but it is. We're taking a positive number, raising it to a power, so it's positive. Okay, so let's simplify this. This is the limit as n goes to infinity of 1 plus 1 over n to the negative n squared divided by n. All right, so because remember, the nth root is the same as taking it to the 1 over nth power. So now we can simplify this. It becomes the limit as n goes to infinity of 1 over 1 plus n to the negative n, which you may be beginning to recognize that this is the limit as n goes to infinity of 1 over 1 plus 1 over n to the n. And do you recognize what this limit is? This limit we know is e. And if you don't know that, you can do L'Hopital's rule on it and figure it out pretty straightforwardly. But since we know that, we'll just say that this is 1 over e. 1 over e is less than 1. So our original series, k goes from 1 to infinity of 1 plus 1 over n to the negative n squared converges by the root test. I'm glad I didn't keep working on the divergence test because it would have been inconclusive, right? If it ended up converging.